Hello everyone, in this video I'll be talking about chemical equilibrium. Reaction dynamics. When a reaction begins, reactants are consumed and products are formed. Eventually, the products can react to reform some of the reactants, assuming products are not allowed to escape. Processes that proceed in both forward and reverse directions are said to be reversible. Dynamic equilibrium is a condition wherein the rates of forward and reverse reaction are equal. At equilibrium, rate of forward and reverse reactions are equal, but that does not mean that the concentration of reactants and products are equal. Equilibrium constant. Even though the concentration of reactants and products are not equal, at equilibrium there is a relationship between them. This relationship is called the law of mass action. For a general equation given as this, where the A, B, C are these lower cases A, B, C, D represents the coefficients of these reactants and products. So we can write the equilibrium constant expression as the concentration of C raised to power the coefficients multiplied by the concentration of D raised to power the coefficients divided by the concentration of A raised to power the coefficients multiplied by the concentration of B raised to power the coefficients. So we can say that this represents the concentration of products over the concentration of reactants. So notes. Reactants. So let's write an equilibrium expression for this reaction. So our K is going to be the concentration of NO2 multiplied by the concentration of oxygen divided by the concentration of N2O5 raised to power 2. So what does this imply? Means that when K is greater than 1, the equilibrium position favors the product. It means that the product, which is the numerator, is greater than the reactants, which is the denominator. When K is less than 1, the equilibrium position favors the reactant, meaning that the numerator, which is our reactant, in this case, is greater than our product. Relationship between K and chemical equation. When the reaction is reading backward, the equilibrium constant is inverted. For example, if we have something that looks like this, so our K forward is gonna give us the concentration of concentration of B to the concentration of A. So our reverse, when we want to write the K reverse or K backward, in this case, our reactant will become our product. So we're gonna have A over concentration of B. We can see that this is a reverse of the K forward. So we can see K backward equals to 1 over K forward. That is the inverse of K forward. When the coefficients of an equation are multiplied by a factor, the equilibrium constant are raised by that factor. For example, if we have this expression, we can see this equation is multiplied by a factor of 2. So the new equilibrium constant will be raised to that factor in this case, which is 2. We have raised to power k and k original raised to power n. When you add equations to get new equation, the equilibrium constant of the new equation is the product of the equilibrium constants of the old. equation. So if we have new equilibrium constant K and 2, the new equilibrium constant will be the product of these two. For heterogeneous equilibria, the concentration of pure solids and liquids do not change during reaction. Therefore, they are not included in equilibrium constant expression. For example, write the equilibrium constant expression for this equation. From this equation, we see that iron is solid and iron 3 oxide is also solid. We are not going to include this in our equilibrium constant expressions. So our K is going to be the concentration of CO2 raised to power 3 divided by the concentration of CO raised to power 3. Equilibrium constant involving gases. For concentration, the concentration of gas in a mixture is proportional to the partial pressure. Therefore, equilibrium constant can be expressed as ratio of partial pressure of gases. For this expression, equilibrium constant is written as this. So because the concentration is directly proportional to partial pressure, we can write the equilibrium expression in terms of the partial pressure. So our Kp is going to be the partial pressure of C raised to power coefficient of C multiplied by the partial pressure of D raised to power D coefficient of D and partial pressure of A raised to power the coefficient of A multiplied by the partial pressure of B raised to power the coefficient of B. Let's take a look at this example. Consider the chemical equation at 25 degrees C of ammonia, production of ammonia. The K forward for this reaction is given as 5.C. So calculate the equilibrium constant for the following reaction at 25 degrees C. So looking at this expression, we can see that the second, this is first expression, and this is the second expression. For this first expression, we can see that the second expression is the reverse of our first equation. So we have ammonia here as a product, and in this case is a reactant. So we're going to write our new K reverse is going to K backward is going to be 1 over K forward. So which is going to give us 1 over 5.6 times 10 to power 5. Right. Taking a look at this expression, we see that for us to have this value, this first expression was multiplied by a factor of 1 over 2. Let's take a look. So for us to have 1 ammonia, this was divided by 2. This is already 1 divided by 2, and this is divided by 2. Right. So when we multiply all this by 1 over 2, we're going to get 1 half and 3 over 2. So this is a factor that we're going to use to multiply the equilibrium expression. So this, our K new, is going to be 1 over 5.6 multiplied by 10 to the power 5. Going to multiply it by half. So this equation, when we plug into our calculator, it's going to give us 1.3 times 10 to negative 3. Calculating Kp and Kr. The Kp and the Kc, Kp and Kc can be related with this equation. Kp equals Kc multiplied by RT raised to power delta N. Delta N is the difference in number of moles of reactants and products. In calculating Kp, partial pressure are always in atmosphere, and Kp equals to Kc when delta N is 0. For example, for this reaction, Kp is given as this. Find Kc. The first thing we need to do is to write our expression, which is given as Kp equals Kc multiplied by RT raised to power delta N. Our Kp has been found. We're looking for Kc, right? So Kc is going to be Kp over RT raised to power delta N. Our R is our universal gas constant, which is 0.08206 liter atmosphere. Liter atmosphere per mole Kelvin. And our T is 25 degrees C. We need to convert this to Kelvin. So this gives us 298 K. Our delta N is going to be the moles of product, number of moles of product minus that of the reactant. It's going to be product minus the reactant. The products we have, in the product we have 2 moles, and that gives us 2, right? Minus, how many moles do we have in the reactor? We have 2 of NO and 1 of oxygen. So that gives us total of 3, right? We have 2 and 1. So that gives us 2 minus 3, which gives us -1. Our delta N is -1. So we're going to plug this value into our Kc. Our Kc is going to be Kp. So Kp is 2.2 times 10 to the power 12 divided by our R, which is 0.08206 liter atmosphere per mole Kelvin times 298 K raised to power -1, which is our delta N. So when we plug this into our calculator, it gives us 5.4 times 10 to the power 13. So this gives us our value of Kc. And I hope that this helps us in solving more problems. Thanks for watching.